Science 30s, Mr. Riley here. Going to put a couple videos here together to review some of the stuff that we did before spring break. So our first one, we're looking at acid-base theories. And first theory is called the Arrhenius theory. And so this guy Arrhenius was trying to explain the behaviors of acids and bases. And what he came up with was that acids produce hydrogen ions in solution, and bases produce hydroxide ions in solution. Now, this was a pretty good theory and explained a lot of acids and bases, but there were some things that were missing. So things like, why ammonia acts like a base. There's no hydroxide there. Or why when CO2 dissolves in solution, it produces an acid. There's no hydrogen there. So Bronsted-Lowry theory, this is the theory that we're going to be focusing on, dives a little bit deeper. It defines an acid as a proton donor. Okay, and protons are just hydrogen ions, right? If a hydrogen atom lost its electron, it would be a proton. And bases are proton acceptors. So we looked at some examples of this before the break, obviously, but let's review. So first one here, I have an acid here. This is acetic acid. And I'm going to explain what happens to it when it's in solution. So water is a funny thing. Water can actually act as an acid or a base in these Bronsted-Lowry reactions. And one thing I'm going to have to look at here for my reaction is acetic acid a weak acid or a weak base? So we look in our data booklet here, and I find acetic acid all the way down here. These are the strong acids at the very top. Anything else is weak. So that means that not all of the hydrogens on the acid molecule are reacting. So we actually get this double arrow, which signifies that there's equilibrium. The reaction is going in both directions. So what we have to look at here is our acid is going to donate a proton to our water. And what we're going to end up with is we're going to have CH3COO. And since it lost the proton, it now has a negative charge, and it's aqueous. And water gains a proton and becomes this guy, the hydronium ion, which in Bronsted-Lowry theory, this is what explains the acidic properties of a solution. So the acid, after it's reacted, becomes its evil twin. It's the conjugate base, and the hydronium becomes what's called the conjugate acid. So that's explaining a weak acid. Okay, let's look at this one. This is a carbonate ion. So this would come from something like limestone rock, like we have it here in Alberta. Calcium carbonate would split up to become carbonate ions. And when those react with water, if these are a base, water is going to act like an acid. And again, if we look at that chart, we're going to see that carbonate ions are a weak base. So we're going to have that double arrow. But in this case, water is going to donate a proton over here. So CO3 2 negative is going to become CHCO3 with a 1 negative because it gained that proton. Okay, and that's going to be our conjugate acid. Okay, and water, H2O lost a proton, has now become a hydroxide ion. And that's what's going to give our basic solution its basic properties. And that is going to be our conjugate base for water. Now, neutralization can also be explained by this. So here I have a weak base, ammonia, and I have a weak acid. Okay, this is carbonic acid. And so the acid is going to donate that proton to the base. So what we're going to get, again, these are weak acids and bases. We're going to have that double arrow. And we're going to get NH4 positive, which is an ammonium ion. So that's going to be my conjugate acid. And then H2CO3, it gave up a hydrogen. So now it only has one. So it's HCO3 negative. And we have here the conjugate base. Okay. So below here, what I want you guys to do is I want you to try these two. So pause the video right now and give these a try. Pause it now. Okay, so I'm going to go over the solutions quickly to these. HCl, if we look up at the table, this is a strong acid. So what's going to happen to it is when it reacts with water, it is going to completely react with water. So we get this single arrow, okay, shows that there's 100% reaction. That's my acid. Water in this case is going to act as though it's a base, and it's going to accept that hydrogen. So hydrogen's coming over here. So we're going to get chloride ions, and we're going to get hydronium ions, and that's what's going to, again, give our solution acidic properties. Okay, this is my conjugate base, and this is my conjugate acid. You guys will notice hydronium is always going to be acting like an acid wherever it is. Hydroxide is always going to be acting like a base. Here's a neutralization. I want you guys to complete this. We got hydroxide here. We have sulfuric acid. These are both strong, so I'm going to put the single arrow here. This is your base. Hydroxide is always going to be a base. This is your acid, so we're going to get a hydrogen ion being donated by the acid to the base, and we're going to end up with HOH, which of course is water, and we're going to end up with HSO4 negative, okay, which is going to be, that's going to be our conjugate base, and this is going to be our conjugate acid. Okay, so there's your Bronsted-Lowry review. Good luck, you guys.